So far, when working with vectors, we've only been working in 2 dimensions, right? We work on our XY Cartesian grid, and we only have 2 numbers when we write a vector in its component form, right? We have the X component and the Y component. But we're actually going to be able to work with vectors in 3 dimensions. Okay, so I'm going to try to help you throughout the course of this video visualize and understand how vectors operate in 3 dimensions. So we have our 2-dimensional grid here, and you can see that we can actually transform it in a way where we now have a 3rd dimension. And when those first 2 dimensions we refer to as X and Y, the 3rd dimension is going to be referred to as Z. So now we have X, Y, and Z components. You can see that in this 3-dimensional space that you can plot a point, for example. You can visualize a vector, and you could even graph lines in this space if you wanted to. For this video, though, we're going to focus on vectors. Now, I'm going to orientate this grid in such a way that our X, Y, and Z axes are orientated like this, and you can see that they're indicating the positive direction. There is a way to remember if you're trying to draw a representation of this 3D space on a flat 2-dimensional piece of paper, and that's using the right-hand rule. If you don't remember the right-hand rule, or if you haven't learned it yet, the idea is that with your right hand, you do as follows. You point your hand in the direction of X, it wraps towards the direction of Y, and your thumb will indicate the direction of Z. And so if I was working in 2-dimensional space and I wanted to sketch this out, I would have a line like this. This is my X. I have my Y, and I can have my Z like this. And I've labeled X, Y, Z on the sides where it is positive. So this is 1, this is 2, etc. Over here you have a Y value of 1, 2, etc. For Z, same thing, 1, 2. You have your negatives, right? -1, -2, -1, -2. And these down here as well for Z, -1, -2. It's getting a little bit crowded now, but you get the idea. It's important that this grid is set up in this way, right? Where you have your X positive here, Y positive here, Z positive here, and this can be rotated. I mean, if you look at the 3-dimensional figure we have here, you can rotate this in different ways, but it's important to be consistent, I think, so that you don't mess up the orientation, so that you don't mess up the relationship or the positional relation between each axis with each other. So again, X wraps towards Y, indicates Z. That's what you want to remember for the right-hand rule. Now, let's say we have a vector. In the past, if you have a vector, we'll call it vector v. You would just have a couple numbers, like 1, 2, something like that. That's because you only have an X and Y direction when you're working in 2 dimensions. But if you're working in 3 dimensions, you would have a 3rd number here, right? So instead of X and Y, it's X, Y, and Z, or Z, right? So you have those 3 numbers. And so if you want to make a sketch of this in 3-dimensional space, you could say, all right, here's my X-axis, my Y-axis, my Z-axis, and try and make this as neat as possible. So your X value is just 1, so X value of 1. Your Y value is 2, so that's a little bit further, 2. And then your Z direction, you're way up here at 3. Now it's very tricky, I'll admit, to plot a point or draw a vector in 3-dimensional space on a 2-dimensional drawing, but you kind of have to do your best, right? So one way to do it is you can, make a line coming from your X and meet with the Y, and you would do that in 2 dimensions typically to put a point there, right? But then you have to go vertically like this until you reach the height of 3 on the Z-axis, and then that point right there, that's the point 1, 2, 3. If you want the vector 1, 2, 3, then you got to start at the origin and you connect to there, and that would be your vector. At least that's one way of representing it. So it's very difficult to imagine, I think for some people anyway, trying to represent this on a 2-dimensional piece of paper. It can be a tricky thing, but that's the process you want to go through. Again, if you're not sure how I'm doing this, look at this 3D representation. This is what I'm trying to draw, right? This is what we want it to look like, okay? Now, what's cool about 3D vectors is that a lot of the things we talked about with 2D vectors, a lot of those concepts will apply to 3D vectors as well. For example, if I wanted to figure out the magnitude of this vector v, right? If I want to know what's the magnitude, or as we discussed, you can think of it as the length of that vector. Well, you can do the exact same thing that we normally do, right? You can say 1 squared plus 2 squared plus 3 squared and take the square root, right? It's your Pythagorean theorem. This also works in 3 dimensions, which is pretty neat. Now, if you do this calculation, you get the square root of 14, which is approximately 3.74 units. So that would be the magnitude of your vector v. So again, the exact same process we would use to find the magnitude in 2 dimensions, except we have to use all 3 of those components when we do the calculation. Okay, what else can we do with these? Well, we know in the past that if you're given the magnitude of a vector, right, and you want to figure out its x and y components, you can multiply by cos or sine of the angle, right? So let me just remind you of that. In 2 dimensions, if you have a vector that goes like this, right, and you wanted to figure out the x component, right? So if this turned into a triangle, if you projected this downward, what would this x component be? And then you can also figure out the y component, right? What this vector would be, just like that. And the way we would do that typically is you'd use sine and cos of this angle, whatever it is, right? You're using your primary trig ratios to figure out those lengths of this right angle triangle. Now, one thing I'll do, instead of having this drawn here, I could also draw that component up here, right? And if I draw it over here, you can make the case that, well, why don't I just use this angle here? I'll call this angle alpha, let's say, and I can just take cos of this angle to figure this out, rather than taking sine of this angle. And of course, sine of theta and cos of alpha will be the same. So let me just elaborate a little bit on what I just said. Try to simplify it anyway. So let's say that this is a vector, we'll call it vector b, right? If I take the magnitude of vector b, if I know what that magnitude is, and I multiply it by cos of theta, what I will get is the x component, right? I will get this length on the bottom. If I take that magnitude b and multiply it by sine of theta, well, I will get the y component, right? But that's not the only way to get this y component. You could also say magnitude of b multiplied by cos of this angle here, alpha. And this would also give you the y component, right? These are 2 different options to figure out that y component, right? Now, why am I bringing this up? Well, because when you're working in 3 dimensions, it's not like you can use sine, cos, and then some third ratio, right? You can't use tan. That gives you something else altogether. When you're working in 3 dimensions, what you want to focus on is the angles that you're using, right? So if you ignore this for a moment, you see that if I want the x component, I have to take cos of the angle made with the x-axis. If I want the y component, I have to do cos of the angle made with the y-axis, right? And so if you're imagining 3-dimensional space, then you can imagine that all you have to do is do cos of the angle where the angle is between your vector and that axis, and you can figure out that component. And sure enough, that's true. If, for example, we have our vector, and I'll use the same vector we used in the last example, where the magnitude of vector v we figured out was the square root of 14, and I'll use that as the exact magnitude in this case. If that's our magnitude, and we want to figure out the components in the x, y, and z direction, all you have to do is take that magnitude, root 14, and multiply it by cos of the angle made between the vector and the x direction. You take the magnitude and multiply it by cos of the angle made between the vector and the y direction, and you take the magnitude of the vector and multiply by cos of the angle made between the vector and the z direction. So this will give you the x component, the y component, and the z component, right? Now we know the x, y, and z components already, right? This should be equal to 1, this should be equal to 2, this should be equal to 3, because remember the original vector, vector v, was 1, 2, 3, right? We know this. And so if you're trying to imagine where these vectors are located, and remember our vector looks something like this, right? Comes out this way and this way, and then it goes up vertically to, you know, a height of 3 up here. That's what our vector was when I drew it earlier, right? Something like that. The locations of all these angles that I've written here, and I'm just using different Greek letters to represent them. You can use whatever you like to represent those angles. They can be kind of tricky to imagine where they are, but remember this is your x-axis, right? This first angle is going to be between the x-axis and the vector. It's kind of on an angle relative to the screen, so it's difficult to see. Now the y-axis here, the angle between the vector and the y-axis, that's the angle you're going to use here. And then the angle between the z-axis and the vector, that's the angle you would use here to find the z component, right? And by taking cos of the angle, multiplying by the magnitude, you would get this vector, you would get this vector, and you would get this vector. And those vectors all have magnitudes of 1, 2, and 3. So that might be a little bit complicated to imagine, but look at it here in three-dimensional space. I've drawn out all the 3 component vectors we have, right? And you can see the actual vector v. Now we know that component vectors you should be able to add together to get to your final resultant vector, right? For example, in 2 dimensions, we know that if you have a vector that goes like this, all right, let's call that vector v. If you have the x component and the y component, you can add those 2 vectors together and your vector v is the result of that, right? I can say vector x and vector y. So vector x plus vector y should equal that total vector there. So put the little vector signs over these, but you get the idea, right? Remember how to do that. Your components should add together to make your original vector. The same is true in 3-dimensional space. If you take these 3 vectors, and I'm going to show you here, I'm going to move them. You can add them up tip to tail. Again, the order that you add them doesn't matter. You will end up in the location of the end of that original vector. And so when you add these up, you get as an answer that original vector. And that brings me to my last point. We can add vectors in 3 dimensions the same way we do in 2 dimensions. Just add the vectors tip to tail. So let's say we have vector A, and vector A can be something like 2, -3, 5. And let's say we have vector B, and vector B is -1, 2, 4. And the question is, what is vector r equal to if vector r is equal to a plus b, right? Vector a plus vector b. What will be the resultant vector? Well, we can simply add the components the same way we would in 2 dimensions, right? You can say that 2 plus -1 is 1. You can say -3 plus 2 is -1. And you can say that 5 plus 4 is 9. So this would be your resultant vector. Now, if you want to visualize this, you can sketch it out in 2 dimensions, or you can use the 3-dimensional model, right? And you can show that, okay, vector A, and then we add to that vector B, and of course the resultant we get goes from where we started to where we ended up, right? We added these tip to tail, and we get our resultant vector. And you can see that in the x direction, it's moving 1 space. In the y direction, it's moving -1. And in the z direction, it's gone a distance of 9, right? So you can see how all those components kind of work together to make your resulting vector. Now, if you want to play around in this 3-dimensional space, you can use Desmos.com and just plug in some vectors and see what you get. It's completely up to you. But you will be asked by your teachers most likely to make some of these 3-dimensional sketches by hand, right, on a paper. So you do want to get used to the idea of being able to make a little sketch, right? Your x direction, your y direction, and your z direction. And again, I've labeled these x, y, and z on the ends where it is positive. So definitely be comfortable doing that and making some pretty rough sketches on there. But again, just try to do your best.